Right, last class we studied some of the equations of the structure of the sun. We found the equation for the mass, the equation of mass continuity, the equation of luminosity, and the hydrostatic equilibrium equation, the equation for the pressure. Missing are the equations for the temperature, the density, and for the nuclear reaction rate. Let's look at the equation for the temperature. The temperature equation shows also when the sun passes from having a radiative zone to a convective zone, or when that is expected in other stars. Stars that are heavier than the sun have a convective core and a radiative envelope. Stars that are less massive have fully convective. So let's see how that comes from the equations. What is the theory behind it? So the temperature equation actually comes from the luminosity. So we know that the luminosity is 4 pi r squared times the flux. So that is the luminosity from the surface. R is the radius of the star and F is the flux at the surface. But we can write the same equation for any shell inside of the star. For any shell at the radius r, you have a luminosity Lr that is being transported through the area of the shell by a flux F. So you can write this equation for any shell. And as it turns out, the flux is proportional to the gradient of the temperature. If the flux is being transported by radiation, the flux is proportional to the temperature gradient. So we can write the flux as a luminosity over 4 pi r squared, and then you have an equation for the temperature. dTdr is proportional to the luminosity on the shell over the area of the shell. And if we can write this proportionality in terms of a constant, then you would have an equation for the temperature. Question is, what is this constant C?